Okay, Assalamualaikum and very good day, class. So, today I just want to make a recap of what I've covered in the previous lecture before the semester break, sorry, before the mid-sem break. So, this is about the interface, the programmable peripheral interface, which interface the I/O um, devices. As you can see here, this is the architecture of 8255A. As you can see here on the left, there's a data line here, D0 till D7, which is 8 bits, and this is the control logic, which comes from the 8085A. And here you can see the bus that goes into uh, different I/O, whether it can be input devices or it can be output devices. So for 8255A, mean this is the external chip that you have to use to interface your 8085A processor and the I/O. So if you want to communicate between the 8085A processor and the input or output devices, we have to use this external chip, which is the number of chip is 8255A. So this is the features of the chip, and they have 24 bits of digital I/O. So it can be two configuration. I mean, you can make it into two configuration. The first one is you can make it you can have four ports, which two ports are 8-bit size and the other two ports are 4-bit size. When this is based on this, you can see here we have four ports here, right? Port A, port C, sorry, we have three ports, yeah. Port A, port C, and port B. So for the first configuration, we can connect it into four external devices. But if we connect it to four external devices, this port C, high and low, will become only 4 bits. The other way to connect it is by combining these two port C, so it becomes 8 bits. So we can connect these two to one device which use 8 bits of data bus. Alright, so that is the first thing. And then the second thing is about the how we address the I/O. So here this is the address AD0 till AD7, which comes from the what I call it, from the 8085. So we take the line out and we connect it here with the address latch here, and also it will also go into here. uh, sorry, this is the address, and should be this is the data. Alright, so for the address, it goes into the address latch, and the address latch output will go into the like one circuit where we call it address decoding circuit. In here, this should be the custom circuit based on the address that you assign in your code, in your assembly code. So because if you remember last time we talk about the addressing, we use 16-bit address for the memory, and for the I/O we are using 8-bit address. So this is the address of the I/O. So here you have to configure the circuit. So if the address that being sent by the 8085A is assigning is what I call is associated with the devices, your input output devices here, then it will trigger this up. The output will be high, sorry, yeah, will be low because it is active low, and will trigger the circuit on. So the circuit will be activated. So whatever address that goes here will will pick whichever I/O that the processor want to communicate with. All right, this is the how we communicate it in term how we communicate with the IO by using the assembly language. So we have to have the base address for the IO. So base address plus 0 is referring to the port A. I mean, after this we'll see some examples what it meant by this slide. And then the second one, base address plus 1 uh, plus 1 plus 1 mean this is referring to address, mean like your base address plus 1 is referring to your port B, and then plus 2 is referring to your port C, and plus 3 is referring to the control where we can what do you call, we can change the setting of the 825A chip. All right, so okay, this is the register where we can set or we can change the setting for 825AA. As you can see for the bit D0 here, if we set it as a 0, then this port C will become as output. If we set it as 1 here, the port C will become input. Same goes as D1 and also D2. And then here is the mode selection, which is we are not really focusing on this type of thing first, but we just focus on here. I mean, to set the port A, port B, or port C to become input or output. So we have to change the setting here. Either we give 1 or we give 0. Okay, this is the example how you can do it in the code. For example, we want to achieve the settings here. So the first one is both groups A and B operate in mode 0. So which is D5 and D6 has to be 0, 0. And then port A and port B, port A will become input, port B will become output. We can see here port A, if it's port A is port A is input. So if port A is input, then it should be 1, and port B is output, it should be 0 here. So that's why you see here we move immediate value 9 1. So if you change 9 1 to binary, 1 here is 0 0 0 1. So 0 0 0 1 here is 1, where we set the port C lower is equal to input. Port C lower, yeah, equal to input. The rest is output, that's why it becomes 0 0. And then uh, 9 is equal to 1 0 0 1. Yeah, this should be 1 and this should be 0 0 and this should be 1 because port A has to be the output. Oops, sorry, no, this is port C. So this is port A. Port A should be wait, port A should be input. Port A should be input. Yeah, port A should be input, so it should be 1. Yeah, that's correct. So this is 9 and this is 1. So this is 1 0 0 1 and here is 0 0 0 1. That is the example how we can set the input. Sorry, how we can set either we want to make the port A B C input or output. I mean that is the setting, and then we send the setting out to F3H. This is the address, or the F0 is the base address uh, for this chip, mean where we mean or mean sorry, okay, come again. So the F0H is the address that referring to this chip where we connect the input and output devices. So the base address is F0, and to change the setting, if you remember here, I mean the control setting is at base address plus 3. That's why we send it to F3. This is F0, so we add another 3, so it becomes F3, I mean which will be sent to the control port. All right, so Okay, what else? Okay, this is another example in how we can make this port A and port C as the output where we connect it to the LED, and here the port C, uh, the lower port C and port B are being connected to the switch where we will control the LED. Alright, okay, this is the example. The first one is the bit that you want to send to the control port. I mean, this is 83, and you send it to the address here, F3, and then you have to read the switches which you already set this F1, right? So if you see what is F1, F1 is the F plus 1 is the port B connection. So port B, you set it as the input. So you are taking the input reading and you send it to the port A. So whatever input setting that you read here from the switches that been connected to port B will give the effect on the port A, which you connect it to the LED. So this is just the example, and you can go through it to understand how you can send the settings to communicate with the input and output devices by using 8255. Okay, this is just the mode which I will not cover in this lecture. All right, what else? Okay, I think that's all just to cover for this part on the 825AA chip. Okay, now we'll go into the interrupt. Okay, class. So now I'll talk about interrupt. Interrupts are one of the most important thing in processor because this is the main tools that we use to communicate with the processor. Because if you want to do like multiple processing tasks, it only can be achieved by having the interrupts. So interrupts is like knocking the door of the processor and telling them that you need something. Yeah, they have to help you with something. So that is interrupt. So just imagine like there's a people that live in a house, and there are a lot of people knocking the door. That means like there are a lot of interruptions from outside, and we have to know the type of interrupts that comes, the type of the people that come and knock the door, so that we can differentiate what kind of service that we can give to these interrupts. All right. Okay. uh, okay, so the definition, you have to read through all the lecture notes. I mean, what I'm trying to do is just to simplify the understanding, so that you can grab what do you call it, a brief idea on what's the thing that we try to learn. But for you guys, you have to go through the whole slide, read line by line, so that you get a better understanding on the subject that we discuss. All right, so here the hardware interrupt is a CPU facility which permits superior asynchronous events to suspend program execution and instead execute the software. So I mean, like what I say, so if somebody, let's say you are doing something, right? You are cooking, and then like somebody is knocking the door and they come and they tell you, okay, something is not right happening. I mean, in some part of your house, or maybe your there's a problem leaking or whatever. So you have to stop cooking and you have to let that people to come and fix the leaking first. Then after they're done with the fixing stuff, and then you can continue to do your cooking stuff. So that is the example of uh, the interrupt. So the connection to the processor which allows external devices to signal a request for service is called interrupt pins. So there will be a few interrupt pins that is connected to the processor. As you can see here, this is the image of the connection. Alright, okay, I'm not sure whether you guys can see it or not, but if you cannot see it, you can download the schematic of 8085, and you can see there will be a few pins that being assigned to for the interrupt pins. I mean, that is what is being referred here. And then okay, the software module that the processor executes in response to an interrupt is called interrupt service routine. So the software module mean when the interrupt comes and telling the processor, okay, please do some service for me. I mean, the software module that the processor will do for the interrupt, we call it interrupt service routine. So we have to know this term, because if you write the code, this is the code that we have to refer to the ISR to service the interrupt. Okay, the interrupt mechanism is such that after completion of the ISR, okay, so after, like what I said, after they're done doing the service for the interrupts, they'll go back and do whatever the job that they did before. Like for example, the cooking example, right? So you are cooking, and one of the guy came to your house and knocked the door and tell you that there's a leaking in your house, and then you have to let them come in and fix it first, and then when they're done, they leave your house, then you continue to cook or continue your cooking. All right, so this is the interrupt event sequence. This is the basic flow, how when the interrupt come and how the processor act with the interrupt. So for example, the first one is just a normal processing, like executing your code line by line, following the flow of your codes, and all of a sudden interrupt occurs, one of the interrupt pins being activated. So then the processor will take action on it. It will save the PC on the stack, which is the program counter, the current address that the processor is executing, and then it will save it on the stack. And then now it start to branch to the ISR, meaning that it take the new address, the ISR, the interrupt service routine, where we'll go to this set of code for this interrupt service routine, and we'll go to another address and do execute the ISR. Okay, when they are done with the ISR execution, it will retrieve back the PC. So whatever PC that they send here, it will be retrieved back and resume the normal processing. It's just a simple procedure how the 8085 service the interrupt. Okay, they are basically, we can say few types of interrupts. The first one is direct interrupts. So the interrupting device need to provide the interrupt signal only to assert the signal to the interrupt pin of the processor. With direct interrupt, the address of the first instruction of the ISR for the particular interrupt is pre-programmed into the CPU. Okay, what happened is that this is direct interrupt, so we have to know. It's not that all of the ISR that you want it to be can be used, can be assigned to these direct interrupts. No, because these direct interrupts already pre-program the address inside the CPU. So this is might be like a special type of interrupts where it already the address of the ISR interrupt service routine is already embedded inside the CPU. And then the second one is the vector. So for the direct interrupts, you just initiate the interrupt pins, and you don't have to give the address that referring to the ISR, because the ISR address is already embedded inside the CPU. For the vectored interrupts, the first thing is that you have to have the interrupt signal and also the 16-bit address for the first instruction of the ISR. Alright, so the main difference of direct and vectored interrupt is that for direct you don't have to provide the address. For vectored you have to provide the address for the interrupt plus the interrupt signals. Okay, and then the other thing we have to know about interrupts is that there are interrupt that is maskable, and there are interrupts that is non-maskable. So what is meant by non-maskable? So non-maskable means that the interrupt will always, if asserted, mean if the interrupts come and knock the processor door, it has to be serviced. So there's no software mechanism to prevent the processor being interrupted by a non-maskable. So that anytime that this interrupt comes, it has to be serviced immediately. But for this maskable interrupt, if asserted, will only interrupt the processor if it is enabled. So you can enable it or you can disable it. If you enable it, we call it unmask. If you disable it, we call it mask, which is done by the software. We'll see in the example how we can set this mask or unmask on this maskable interrupt. So most maskable interrupts automatically become disabled after an interrupt has occurred. If one interrupt occurred, and automatically all of these maskable interrupt will be disabled, so that the what they call it, the CPU can finish servicing this the interrupt service routine for the current interrupts. All right. Okay, so the interrupt priority, as we have we need to have like many kind of interrupt. So but what happen if there are two or three interrupts that come at the same time? So that's why we have to assign the priority for each interrupt. So this is the interrupt pins, I mean, where you can see it on the 8085 A schematics. I mean that there's like a trap interrupt pin, RST 5.5, RST 6.5. So and this is the type, whether it's a direct or vectored interrupt, as you can see. So this is a vectored, and most of the what do you call it, the interrupt is direct. And this is the whether the interrupt type can be maskable or unmaskable. So as you can see here, I mean, these are the pre-assigned address for this type of interrupt. So if you want to use this kind of interrupt, I mean, these are the addresses that you have to use. And with the INTR interrupt pin, you can set, this is a vector that you can set in the code, and this is the priority. As you can see, this is the highest priority. So if there are two interrupts come at the same time, for this one, RST 5.5 and RST 6.5, which one will be service first? This I'm not sure why 4 is here. So I mean, if we follow the number here, so the 3 will be service first, and then the processor will service the 4 priority. All right, so okay, this is uh just the trigger type. I mean, this is more on the current level, how we can trigger the interrupt. All right, so okay, this is the example in how we can enable or disable the maskable interrupts. All right, so these are the pins, right? Okay, wait, wait. Let me. Okay, sorry. This is the register that where we can set the setting. So these two we will not cover in our courses. The most important thing is here how we can enable or disable the type of interrupt here. So this is the register. As you can see, this is the example. For example, we want to enable RST 7.5 and RST 5.5. which is 7.5 and 5.5, and disable RST 6.5. So they send a signal 0 1 0. So 0 here means that it disable the mask, and then here enable the mask. That means when it disable the mask, it become unmasked. So when it become unmasked, then that means it's enabling the direct interrupt for this M5.5 and M7.5. All right. Okay, this is the another example. I mean, when they already said enable the ISR 5.5 and 7.5, we have to write the interrupt service routine for both interrupts here. All right, and yeah, here is the the address, right? Okay, let's see. Yep, yeah, this is the address that referring to the interrupts. Okay, what else? Okay. All right, I think I'll continue covering about this. I'm not sure. Is there anything more about interrupts? Okay, no, I think that are only some of the most important part that you have to know about interrupts. And after this, I'll make a lecture explaining about one of your lab module, which I think is quite important. And then after that, I'll continue with another lecture. All right, thank you guys.